All right, so let's get started. So thanks for having Matteo and me. This is we're doing this together, but maybe more people will join. Hopefully, it's a wonderful experience to collaborate on this. So the topic is parameterized lenses and servers. And the point, like the main motivation behind this, is that if you've ever written a server, it's a lot of work and it's really difficult. And sometimes it would be nice if the computer could do more work for you. And so this began by just writing a library where the computer would do more work for you. And what does this work look like? Oh, this is going to be the structure of the talk. So I'm going to start with explaining how servers work, and then we're going to interleave how this maps into dependent lenses and lens composition. So first of all, a server. Usually, the way you use a server is by calling into it. You call an API. The server exposes an API, and then you send requests to the server, and the APIs describe what kind of requests the server expects. So here, for example, I have different kinds of methods that you can describe in your requests, and they all go into a URL endpoint. And you can see that the URL endpoints are all the same, but the methods are different. That's because they have different semantics. So get is used in order to obtain some data from the server, but post is used in order to update some data on the server. And similarly for delete and put, delete removes something from the server, and put adds something to the server. You can already see that something that's going to come later. Those three things, we can think of them as things that change the state, and we can see this as something that queries the state. If we look at the server from the perspective of its API and of a user of the API, you can see each endpoint as a function where you provide some information and you obtain a result from the server. So everything that's on the left here, on the left of the arrow, comes from the client, and everything on the right of the arrows comes from the server. So if you want to obtain, for example, a to-do item or a list of to-do item, you have to provide an integer which represents an ID. If you want to update a to-do item, this is, sorry, I didn't say, but this is assuming that the server is a server that implements a to-do app. So you have to-do items, you can tick them off, you can add new one, you can remove old ones, etc. So changing a to-do item requires two things. It requires the ID that you want to change and the to-do item that you want to change. So what is different about it? Delete is just delete one of them, and put is add a new to-do. So they have different type signatures because they do different things. And if you model this as some sort of interactive system and use one of those interaction graphs, you have the client on the left saying, at some point, please get me something, and the server will say, here it is. So here you have a small interaction where you send something and you get something back. And here you have another interaction which says, well, now that I've learned something about it, I know which to do it is, let me use this to change it, and I will change it in this way. And the server will say, okay, I'm done. And so with this small interaction, we can already see this duality between, well, duality, this pairing of things that we obtain and things that we change. First, we obtain some data, and then we can use this data to update something that we learned about from the server. So now I'm going to pass the pen to Matteo, talk about dependent lenses.
Right. So the structure that Andre found out that get and post have is known as the structure of a lens. And a lens can be easily generalized to a dependent lens, so we'll see why we need this generalization. So what's a dependent lens? A dependent lens is a morphism in a category which is also known as the category of containers or the category of polynomial functors. We'll talk about dependent lenses in this talk, so we take this perspective. And a dependent lens then is a morphism between pairs of, we could call dependent sets. So first we have a type x and a dependent type over x. So for each little x, we get a type, okay? And we could think this as for each request that a server receives, there is a possible type of responses. All right. And what a dependent lens does is map uh, first x to y, and then in the other direction, we map, given an x that we remember ideally from the first step, um, and given an r, which is over the view applied to x, we give an s of x back. So we can picture a lens with this in this fashion. So the view is going in this direction from x to y, and then the update are actually a family of maps indexed by x, which to each fiber over y give us a function in the other direction. All right. Indeed, there is a known correspondence between index sets. So sets which are given like this, and bundles, which are sets or families of sets, which are given like this. Okay, we go in this direction by taking the sigma types, so summing all the sets that this function gives us and projecting back, looking at the index. And the other direction, we construct this functor by looking at the fibers over a given element. All right, so this is the picture we should have in mind. So I have this light because I'm gonna maybe confuse the two because they are corresponding. So just to give you an idea what is the correspondence and refreshing this. So we should think of a dependent lens then, and we can think of it in three different ways. So the first is like the way you would write it in a programming language. So it's just a pair of functions like this. Okay. And the second, if we adopt the point of view that dependent pair sets are actually bundles, then we can see that a dependent lens is this funny diagram like this. So first we see that there is a view going from x to y, then we pull back this bundle along the view, and we get this object here, and then the update maps this stuff to an S, which is over the same x we started from. And finally, the way that I prefer is to draw these objects as string diagrams. Okay, so these are really string diagrams for non-dependent lenses, but the idea works the same. And we can easily see now here that what we're representing is a bidirectional transformation. So x is entering here and being transformed to y's. We remember the x we received, and then later on, ideally here there is an environment that answers. Later on, we convert the answer and um, the x we remember to an answer for the left boundary of the world. Okay, so how does this pertain servers? All right, we can see a dependent lens as some kind of communication node in a network. Okay, and so something like this is converting messages coming from a client to messages arriving at the server, and then it's converting back responses received from a server to responses received in a client. Okay, so this gives us some way to look at dependent lenses. So we can say that dependent lenses, we have a trivial left boundary, are like clients because the only thing they do is sending requests and receiving responses. Whereas lenses that have right trivial boundary are like servers because they receive requests and send responses. Okay, so in some way this is where the bending of the wire happens. Okay, so it converts requests into responses. All right, and channels are like these intermediate nodes, like routers in a network, which converts a request into new requests and do some kind of middleman job. Let's go on with Andre.
Right, so we're going to see very quickly how this is very concretely implemented as a server. And for this, we need to notice a difference between taking the view from the client of what a request is and taking the view from the server of what a request is. So we said earlier, if we look at requests and endpoints, and we map their type signatures, we can see that gets have on the left what the client provides, and on the right what the server returns. But if we take the view from the server and we think about this endpoint as something we have to implement, so imagine that now this is a type signature and you want to implement the function that goes here, you can't do it. And the reason you can't do it is because you are missing some crucial information about the states, right? If you're given an int, an arbitrary int, you cannot infer which to-do item it corresponds to. You have to look it up from a state. And this is what the actual implementation of this server endpoint looks like. So it is a little bit different in that it has this element of state that's been added in. And what it does is that the same thing as before, it takes the ID from the client, but it looks up the states to return which to-do item to return. And similarly for post, we have an ID that represents which to-do item to change and the to-do. But if we consider this as an entire type signature of a program we need to implement, we're stuck because of two things. Because first of all, we don't know which to-do item this corresponds with, and we don't know what's the end state after we've performed our change. This, if we didn't have any additional information, would be a function that returns nothing. It only returns unit. It only does nothing. It's a constant function. So again, to fix this, we add some element of state here that we're going to query, and we are going to also add an element of state, which will be the states after the change has been performed. And again, the way this is implemented is as an insertion into the database, or in that case, it's a list. And that's a very natural implementation for a server, right? But what we've done is that we've changed our signature from this to that, and from this to that. And indeed, there is a very particular, like a very precise way to extend the definition of those type signature is that we're going from plain lenses into parameterized into parameterized lenses. So we have those parameters here where P defines the states before the query or before the request, and Q defines the state after the change has been performed. And so if we take our endpoints before, we see that it has those parameters where the state before and after both are database states. And then those types represent the lens operations performed, as in we ask for it to do by looking up its ID. We are returning to do when requiring it. We are modifying to do items, and when we confirm the modification, we just return a unit.
So, what Andre explained us is basically that dependent lenses are fine if we just model communication, but are not fine if we want to model stateful communication. So a server is not just something that answers a request with a response, it's something that also usually stores some state, and in order to answer a response, has to query that state. Luckily, we have the right mathematical facilities to model this as well, which are parameterized dependent lenses. So para is a construction that emerged recently in the field of categorical cybernetics, in particular for compositional game theory. And what it does is takes a category and turns it into a new category where morphisms are between two chosen objects also have an additional choice of parameter space, which we should think of as like some kind of state or private information that that morphism has access to in addition to the input. All right. So when we apply these construction dependent lenses, we see that we get something like this as a result. Okay, so generic dependent lens now has not only an input coming from the network in this case, but also something private which we have access to, and which also the update has access to. Okay, so now the update depends not only on the request of the client, but also on the state of the server. And what we give back is not just a response to the network, but also an update of the private state. Okay, so in this sense, now a dependent lens represents a stateful channel of communication. And this is now the client server picture that we have in mind. So a client and a server are paired into this interaction, and in addition of the requests and the responses that they send to each other, there is a database, um, which is represented in the vertical direction, which gets queried and updated each time a message is passed around. And we also could think of adding something like this to clients, because also clients store state, okay? But it's less crucial for them, because what really is coordinating all the clients is the state in the server.
So now the question is, how do we use this to make our servers extensible? So we've seen that, so we can define endpoints as function signatures, and we can change those function signatures so that they can be implemented by a server, by a parameterized lens. And then if we do that, each of our endpoint is its own little lens here. And now we recover our description of a server from earlier, which is a server is a collection of endpoints, which describes its API. But what we want to do with this is, again, remember the original motivation is to save ourselves some work. And one way to save ourselves some work is that we don't have to rewrite every single endpoint if we can just extend an existing endpoint, or if we can combine two existing endpoints. And the way we do this is by doing lens composition. So here, for example, I've defined a bigger server where I'm going to recall this graphical representation where you have the wires coming in and out here, where each endpoint has both a, well, each lens has both a get and a post endpoints attached to it, which represents those wires here. And if you want to create a new endpoint, you can simply attach a lens either before or after it, but in general after, so that you can access, for example, more precise parts of the state or more precise parts of the data that you return or modify. And additionally, something that was missing in the original implementation but dependent parameterized lens give you is this ability to stack uh, a composed endpoint with another endpoint here using this operator here, which requires everything, which requires dependency and parameters. And why does it require dependency? Well, it does require dependency because if you describe a server as this composition of all of the lenses that describe all of the endpoints, and you call one of the endpoints, you have to know what is the expected return type for this endpoint. So if you do get endpoint number 2, you know that you're supposed to get the results of this part of the endpoint and not this one, let's say. And so this is why we have this dependency, because the return type of each endpoint depends on which one you've picked. Either this one, this one, this one, or this one, right? And this is bringing us to our definition of how to combine those things. So here we have an example of two endpoints, one of which is our create and is access and update a to-do item, and the other one is create a user. And if we use dependent parameterized lens, the type of this gigantic server is this type signature. So we see that we simply sum our inputs and the output is dependent on the input. And same thing for the second part, which updates the data. And the states are producted together, but in this case, it doesn't change because they have the same internal state. But that would be relevant if you were to combine multiple servers together, for example. So now, Matteo, explain how this works.
So how does this ampersand operator arise? So as Andre already anticipated, this is due to the particular structure that we have in the category of dependent lenses. Okay, so there's a particularly abundant supply of monoidal products. So we have three at least. So the first is the one that we expect in a sense, which is if I have two channels, then I can consider them together and consider them as being wires running in parallel. Okay, and the same happens for nodes which are connected to parallel wires. Okay, so if I have something that goes from x to y, and then something that goes from x prime to y prime, then I can combine it and consider them as parallel nodes. And the same happens for the backward part. Then there is a coproduct. A coproduct is a sort of alternative. It's a split. Okay, so we can either have something going in this channel or something going in this channel. Okay, so what happens if the previous one was multiplying the basis and the total space, so both the request and response space, this is summing them. Okay, so if we get a request of type X, then this is going to give back a response from that kind of request, and vice versa. And at the level of morphisms, this is equally trivial. So this we just do either one or the other. Okay, no surprises. What's interesting is the product structure. The product structure is indeed taking the product of the base spaces. So the product channel is a channel whose requests, whose forward messages can be of both types, x and x prime. Oh, there's a prime missing here. But the answer is going to be of only one of the types. Okay, so this is the either operator. And given an x and an x prime, so given two requests, we are going to answer just one of them, okay, with the correct type, but only one of them. And indeed, we can see that if we have a pair of nodes from this node to this and this to this, then indeed the view part, the forward part, is going to be multiplied together. So we're propagating both requests, but at some point a choice will be made, and that choice will determine which of the updates we actually call. Apart from these monoidal structures, we also have sequential composition, just you wanted to show, because as Andre showed, we cannot, we can stack different endpoints, but it's nice because we can also mount servers at different endpoints. So if we have a user endpoint, then we can mount another server which deals with whatever is concerning users. Okay, and when we do this, what's happening at the level of lens is that the requests we receive, are going to be deconstructed by this stack of lenses, and the responses are going to be built. Okay, so if we get a user, here we extract the to-dos, here we added a new to-do, and here we return that to-do together with the user it belongs to. Okay, but now let's go to parameterized dependent lenses. So in this category, which is built from dependent lenses, but it's a different category, we still have a parallel product. So if we have stateful channels, we can still like consider them together and everything is happening at the same time. So we consider concurrent channels. But now we have this ampersand, which is different from the coproduct and is different from the product that we had before. It's a combination of both. Okay, so let's look at the definition. So if we have a stateful lens, so the parameterized lens, and another one, what we do with the ampersand is we take the Cartesian product of the parameters, and so substantially we take the coproduct of the two interactions, okay, of f and f prime, the two lenses. What this means, if we unpack then the type of this composition, is that the state that we have available is going to be the state that we would have with a concurrent composition. So the server is prepared to serve both stuff from the endpoint P and both stuff from the endpoint P prime. Okay. But the client now has a chance to choose which kind of endpoint they want to query. Okay. Because we are summing stuff here. So here the client is going to provide either a request of type X, for example, of endpoint 1, or a request of type X prime, so a different endpoint. And now when the client does this, the whole parameterized lenses switches binary and decides which track they actually want to run. And therefore now everything is going to follow this. And since we are prepared to serve both endpoint 1 and endpoint 2, we can do this. Except that now when we give back a request, a response, the update for the state, so the database, for example, the server, is going to be of only one kind. Okay, I'm not going to update both, uh, like both the data structures pertaining to two endpoints. I'm going to update just the one that I was actually uh, queried to be updated. Okay, so this is a kind of demonic choice operator, which is putting stuff together, but it's leaving the environment to choose which of the two options which are actually run. All right. And this operator is funny because we found this operator in unrelated work in open games. And then after Andre gave his talk in July, I think, I was like, oh, I know that. I know that operation. So this is basically the same thing we see in games, because I guess it's still interaction structures, but applied to a different context.
So this is basically what we set out to explain. So what are servers? Well, what is the motivation? Then how to improve servers, and then what actually is hiding behind those the server interaction and those abstractions. And the way this manifests is in a library written currently in Idris 2, which allows you to describe endpoints in terms of lenses and then stick on other lenses to describe new endpoints. And this way, the only thing you have to do is describe one endpoint and then stick on a lens which has the correct type to work with it. And this means that when your endpoint is relatively trivial, while your implementation is also relatively trivial. And now what we're doing is that we're improving this library so that, well, this is more of a theoretical concern, but we can lift those endpoints into container morphisms by using exactly the description that we just made earlier about the fact that those are basically lenses, but they are also dependence power lenses. And because they're dependents, there's no reason to stop ourselves from having dependent endpoints. Or say, for example, when we paginate something, you say ask for the next 20 items, you get back a vector of 20 things. Another thing that is in the works is try to find a way to describe your endpoint as a massive tree, which would be all the endpoints and all the endpoints and all the paths through those endpoints, and from this generate the lens that would implement such a server from its endpoint tree. And now the future, which is the thing that we don't actually know if it's going to work at all, but it would be really great if we could make it work. So the first one is it would be one of the things that you have to do when you write servers is error management. And it would be nice if you could know in advance, or if you could have an automatic way of generating errors either at compile time or runtime when you do something that doesn't make sense in the protocol that you're implementing while writing your server. So for example, if you write a shop and you try to check out while you don't have anything, well, you don't logged in or not, don't have a credit card, or you not don't have anything in the cart, this would be an error. So find a way to expose those errors either in the type system or as a runtime construct. That would be useful. And that's wait, we're thinking that if we can map this into some form of session type, that would do it. We'd be happy with that. The other one is if the people who are keen on using the poly interpretation of containers, they will notice that we're not using them to model the entire interaction system. We're only using them to describe static properties of the server, but they're the same mathematical object. So the question is, can we find a way to describe both the API and its interactive model, for example, as a string diagram, using both containers? And the last one is the state. So currently the state is just state, but that's not true. In most cases, state is a database, and database themselves have a lot of lensy operations, right? You select something from a field, or you insert something into a database, and those also look like view and updates as a lens operation. So can we also lensify the state parts of the database of the server interaction? And this way, if we can have well, if we can have those two things, we can have basically everything that describes a server in the same language. And that would save us a lot of effort in both, well, writing all the middleware necessary and also gluing it together.
And that's it. Thank you for your attention.
Thank you.